Here is our next differentiation rule in section 3.3. This one is called the product rule. And here is the product rule statement. We are going to be taking the derivative of a product of two functions. So we've got two functions that are multiplied together, and we are taking the derivative of that combination there, that product. So the derivative with respect to x of f of x times g of x is going to be, and brace yourselves because this is a little bit of a long formula, it is f of x times the derivative of g of x plus g of x times the derivative of f of x. Okay, and there are probably some creative ways to memorize this rule, but you do need to memorize it one way or another. The way I memorized it back in the day is pretty boring. I just learned it as the first times the derivative of the second plus the second times the derivative of the first, where first and second are just referring to the functions there. But again, there are probably some more creative memorizing strategies for that, I'm sure. If you just Google them, I'm sure someone has come up with something better than that. But I go, yeah, first derivative of the second plus the second times derivative of the first. So if you hear me saying that, that's what I'm getting at. Okay, so this is the product rule statement. And now, just like our previous properties and stuff, we are going to prove this just to verify, just to make sure. So for our proof, we are going to start with saying we are taking the derivative of a product. Okay, so derivative with respect to x of f of x times g of x. Okay, and just like our other proofs, we've got to go back to the definition of the derivative to investigate this. So that'd be the limit as h approaches 0 of the function with x plus h plugged in there. So we're going to put f of x plus h, g of x plus h first, and then minus the function with just x. So our function overall is the product of those two, f and g. So we write f of x, g of x, and we put that all over h. Okay. So now for our next step in this proof, because we've just got the definition written down here, we're going to keep that limit as h approaches 0, but we are going to incorporate a very sneaky trick here. Okay, so we've still got our f of x plus h, g of x plus h. But here's the sneaky trick. In the middle of this numerator, we are going to add and subtract a term, the same term, so that ultimately we're changing nothing here, but we are going to write minus f of x plus h times g of x. Okay, so this is a new thing we're introducing into the expression here. And we've subtracted that term, and then immediately we're going to add the exact same thing, f of x plus h, g of x. That way we can say, okay, essentially we changed nothing right there. And then we're going to have our minus f of x, g of x on the end. So minus f of x, g of x. All of that over h. Okay, so I'm going to, just for the proof's sake, I'm going to highlight this little thing we did there and label it as a sneaky trick, because it really is. The folks who initially came up with these rules and these proofs, I have so much respect for them, because I don't know if personally I would have thought to do something like that, but it turns out that is a crucial step in this proof here and really helps things flow a lot smoother. So massive respect to whoever came up with this. Okay, so we've got our limit as h approaches 0. And next, we're going to use a little bit of grouping here. We're going to group together the first two terms in the numerator, f of x plus h, g of x plus h, minus f of x plus h, g of x. And we're going to make that its own fraction or own rational expression over h. And then we're going to add the rest of our terms as their own fraction. So we're splitting the single fraction into two. Here's f of x plus h, g of x, minus f of x, g of x, all over h. So they've got that common denominator of h. That's what allowed us to split this up into those two expressions. Okay, now in each of these new rational expressions here, we're going to be able to factor something out in the numerator. So keep writing your limit as h approaches 0. In the first expression, we have f of x plus h that we can factor out in the numerator. F of x plus h times g of x plus h minus g of x all over h. I'll put this as parentheses there. There we go. I pulled the f of x plus h all the way out of the rational expression, like f of x plus h over 1. And we'll see why in just a second. Okay. Similarly, in the second expression here, we're going to factor out g of x from that one. So we got g of x times f of x plus h minus f of x over h. Okay, so you might be able to see what I'm starting to do here, but we're going to separate this limit of the sum of these two different things into the sum of two different limits. That's a limit law. We've used this relatively recently in a previous proof. So we've got our limit as h approaches 0, f of x plus h, and then g x plus h minus g of x over h, and then plus another limit as h approaches 0, g of x, and then f of x plus h minus f of x over h. Okay, so yes, I know it's kind of a lot. The good news is you won't be expected to reproduce this proof from scratch. So we're just doing this so that you know where this rule comes from, and you can see that it's not just plucked out of midair. There is an actual reasonable proof basis for this product rule. Okay, so we've got now in each one of these limit statements, we have a product. Okay, time for another limit law. So the limit of this product here, we can make into the product of two limits. All right, limit as h approaches 0 of f of x plus h times the limit as h approaches 0 of g of x plus h minus g of x over h. And then same exact thing on the next one. Take this limit of a product, turn it into the product of two limits. Limit h approaches 0, g of x times the limit as h approaches 0, f of x plus h minus f of x over h. Ta-da! All right, so we've broken this down quite a bit here now. And we can evaluate now each of these limits, or maybe not evaluate, but see what each one of these is really. Okay, the limit as h approaches 0 of f of x plus h, that one, there's actually no issue with direct substitution here. So for this one, we can just say this is f of x plus 0 and see that that's just f of x for that limit. Okay. Now for this second bit here, limit as h approaches 0, g of x plus h minus g of x over h. Hopefully that looks a little bit familiar because that is the definition of the derivative for the function g of x. So this is the derivative with respect to x of g of x. Okay. Next, we've got our limit as h approaches 0 of g of x, and that one, well, there's not even an h in that statement, so this is just going to be g of x. As h approaches 0, g of x doesn't really care. It's still just g of x. Okay, so we've got g of x, and then this last one you should recognize, that's the definition of the derivative of f of x. So this is d dx of f of x. Okay, so when we write down what we've gotten there, we have f of x times the derivative of g of x plus, over here now, g of x times the derivative of f of x. And that, my friends, is the product rule statement right there. The first function times the derivative of the second plus the second function times the derivative of the first. And we can see that that verifies this product rule. Okay, so there it is. Memorize that one.